All right, this is section 5.1, video number 2. So we started learning how to take the area, find the area in between two curves that are not specific. One of them is not specifically the x-axis. So if we want to find the area between the curve y equals x and y equals x squared, granted we could go ahead and sketch the graph. There's nothing wrong with that. But I'm going to show you a different way to do it so that we don't have to necessarily sketch the graph. So in this case, they actually gave us the bounds x equals 2, x equals 4, which is good because y equals x and y equals x squared do not meet at those two bounds, so they have given us the bounds. So if they gave us the bounds, at the very least, we know we can start off with an integral from, 2 to 4. I just said 0 to 2, that's why I started writing it, from 2 to 4. Now the question is, which one is the greater function, which one is the lesser function? Because I know I have to do the greater minus the lesser. So the easiest thing to do is to take a number in between your two bounds, such as x equals 3. It can't be one of the bounds necessarily, especially if those happen to be the intersection points. In this case, it technically could because those are not the intersection points. But in the case where the intersection points are your bounds, you want to take any value in between those bounds and plug it in for both functions. Whichever one is the greater value, that's the one that goes on top. So if I take 3 and I plug it into y equals x, for x, it's going to be 3. If I take it into plug it into x squared, it's 9. So x squared is the greater function. So it would have to be x squared minus x dx. And then we can just go ahead and do our standard procedure. 1/3 x cubed minus 1/2 x squared. And we will plug in 2 and 4, and we will subtract. So plugging in 4 cubed is 64, so you're going to get 64 thirds minus 4 squared is 16, but half of that is 8, minus 2 cubed is 8, so that's 8 thirds. 2 squared is 4, but half of that is 2. Now, I am fond of combining kind of the like terms first. So 64 thirds minus 8 thirds is going to be 56 thirds. And then I'll do the -8 minus the -2. So -8 minus minus or plus 2 is -6. Putting 6 into terms of thirds is 18 thirds. So 56 minus 18 is going to be 38 thirds. And again, I strongly suggest practicing the mental math. If you make mistakes here, better than here than it is later on. So practice it now. All right, so let's find the area between the curve y equals x squared minus 4x plus 3 and y equals negative x squared plus 2x plus 3. Got two parabolas here that we want to find the area between. These are both solved for y, so we're good. These are standard parabolas. Let's just go ahead and set up our integral. Integral will go from 0 to 3. Now let's take a value in between 0 and 3 and plug it in and see what we get. So I'm going to take an easy value like 1. If I plug 1 into the first one, I'm going to get 1 minus 4, which is -3, plus 3 is 0. Then if I take 1 and plug it into the second one, I'm going to get -1 plus 2, which is +1, plus 3 more is 4. So the second one is the greater of the two functions. So it'll be -x squared plus 2x plus 3 minus x squared minus 4x plus 3 dx. And then once again, I strongly suggest combining all like terms first and simplifying the integrand. So the integral from 0 to 3. -x squared minus x squared is minus 2x squareds. That takes care of those. 2x, and by the way, you don't want to scratch these things out under normal circumstances. You want to leave all this stuff there. 2x minus 4x is plus 6x. And then 3 minus 3 is 0. Perfect. Gone. But now you can see why it would be best to simplify, because that simplified quite nicely. Less antiderivatives to have to worry about. All right, so antiderivatives now. So negative 2/3 x cubed plus, that'll be x squared, so that'll be 3x squared, evaluated from 0 to 3. Nice thing is plugging in the 0 is going to make that whole part go away, so it's really just plugging in the 3 here. So if I plug in 3, we're going to get 3 cubed, which is 27, negative 2/3 of 27. So I'm going to divide by 3 first. So 27 divided by 3 is 9, times negative 2 is negative 18. And then plugging 3 into the second one, 3 squared is 9, times 3 is 27. And I already know that plugging in 0 makes everything 0. So negative 18 and 27 is 9. And there's the area between those two curves. Okay, moving on. Okay, you may not have seen something that looks quite like this one because it says f of y. That just means that y, in this case, is the independent variable. F of y, just like if you had f of x, we could change f of x to y. Well, f of y, you could very easily just change to x to make it look easier. So I can say x equals y squared and x equals y plus 2. Both of these are solved for x, so we know this is going to be something in terms of y. So I'm going to have to find the y bounds, which means I will set each of these things equal to each other. And this is a quadratic, so I am going to subtract the y and the 2 to the left so I can get one side equal to 0. And then a little bit of factoring. That's going to be y minus 2, y plus 1. So y is either going to be 2 or negative 1, and that gives us our bounds. So now we can take the integral from negative 1 to positive 2. Which one of these is the greater function? Take something in between negative 1 and 2, for instance, 0. Anytime you can use zeros or ones, they're the easiest thing to plug in. If I plug 0 in for y, I would get 0 here, and I would get 2 there. So the y plus 2 is the greater function. So it's y plus 2 minus y squared dy. Okay, nothing really to simplify, so we're just going to take antiderivatives. So we're going to get 1/2 y squared plus 2y minus 1/3 y cubed, evaluated from negative 1 to 2. So let's see, plugging in a 2. 2 squared is 4, half of 4 is 2. 2 times 2 is 4. 2 cubed is 8, so that's going to give us minus 8/3. Minus. Plugging in a negative 1. Negative 1 squared is 1, so half of that is on 1/2. 2 times negative 1 is minus 2. Negative 1 cubed is negative 1 times the negative 1/3 is positive 1/3. All right, so we're going to get, let's see, 6 minus 8/3 there. Minus, a half minus 2 is going to be negative 3/2 plus 1/3. Again, you can do this in any way that you want to as far as adding these things up. I just choose to try and combine the like denominators first. So I've got a minus 8/3 minus 1/3. That's minus 9/3, which is nice because 9/3 is 3. So 6 minus 3 is going to be 3 minus a negative 3/2. So 3 plus 3/2 is going to be 6 9/2. So 9/2 is the area in between those two curves. Okay, let's keep going. This one right here is not as easy to see. Find the area between f of x equals 1 over 1 plus x squared and g of x equals x squared over 2. All right, well, it says the area between those two curves, so we do need to figure out where they are bounded. So I do need to set these two things equal to each other. All right, in order to solve this, I'm going to probably want to cross multiply. So 1 times 2 is 2. 1 plus x squared times x squared is going to be x squared plus x to the fourth. All right, so we have to try and solve this thing somehow. So I'm going to go ahead and subtract 2 on both sides, reorder the right so that the fourth power is the first one there. And you get x to the fourth plus x squared minus 2. Now, believe it or not, this one factors just like a quadratic. This is what is called quadratic in form because the first exponent is double the second exponent, and then I have a constant. So it will factor just like a quadratic does. It just means that my first terms in here, instead of x and x, are going to be x squared and x squared. My factors of 2 are 1 and 2, and they have to be opposite in sign. The greater one has to be the positive to get me the plus x squared in the middle, so the plus goes with the 2, the minus goes with the 1. Now, can we factor any further? Well, the x squared minus 1 can factor to x plus 1, x minus 1. The x squared plus 2 cannot factor because it is a sum, not a difference. So either x is going to equal negative 1 or positive 1. X squared plus 2 can never equal 0 because it's x squared, a positive value, plus 2, another positive value. It will never equal 0. So I've really only got 2 values. My 2 bounds are negative 1 and 1. So now we can go ahead and set up the integral from negative 1 to 1. Again, plug something in between those 2 bounds into both functions. If I take a 0 and plug it into both functions, f of 0 is going to be 1, g of 0 is 0. So the first one, f of x, is my greater function. 1 over 1 plus x squared plus, and you might want to rewrite x squared over 2 as 1/2 x squared just to make it easier to take your antiderivative. Okay, so one of the main reasons this problem was here, because you might look at the first part, 1 over 1 plus x squared, and say, how am I supposed to take the antiderivative of that? So this is one that you're going to have to recognize. 1 over 1 plus x squared is the derivative of the inverse tangent of x. Okay, we haven't used it an extremely large amount yet, but it will start coming up more frequently. So you will need to recognize 1 over 1 plus x squared as the derivative of inverse tangent of x to know that when you take the antiderivative of it, it's inverse tangent of x. Second part is pretty standard. That's just going to be x cubed. Remember that dividing by 3 is multiplying by its reciprocal 1/3, so a half times a third is a sixth. And then we will evaluate from negative 1 to 1. All right, so we get the inverse tangent of 1 plus 1/6 minus the inverse tangent of negative 1 minus 1/6. Now we have to be good with our unit circle stuff and inverse tangents and inverse functions for trig. Inverse tangent of 1 is basically asking us tangent of what value gives me 1, or what angle. And that angle was pi fourths plus a sixth. Inverse tangent of negative 1 is saying tangent of what angle is going to give me negative 1. Now you do have to remember that tangent has a restricted domain, inverse tangent has a restricted domain of only values between negative pi halves and positive pi halves. The right 2 quadrants, if you think about that, of the unit circle. So negative pi halves to pi halves. So this one is actually going to be, instead of pi fourths, it will be negative pi fourths, because it is the pi fourths that would drop down into the negative first quadrant. And then, of course, minus a sixth. So we're going to have a pi fourths minus pi fourths, which is plus pi fourths. That's 2 pi fourths, or pi halves. And then 1/6 minus 1/6 is 2/6, or 1/3. Okay, you don't really need to simplify that any further. All right, there was a lot going on in that problem, and I like that problem because of the fact that it's introducing some more algebra that we haven't seen in a while, and definitely recalling some of the antiderivatives and evaluation techniques that we need to remember. All right, really we just have two more examples left. So number 8 says, find the area bounded by 4x plus y squared equals 12 and y equals x. This one might be more challenging to think about because the y equals x part doesn't really tell us, do I solve for y or do I solve for x? Because it's technically solved for both. It's the other one that's going to tell us that. You don't really want to try and solve for y in the case where you have y squared. You want to try and solve for x because it'll be a parabola which opens to the right. So we want to solve that first equation for x. So we'll have 4x equals 12 minus y squared. And then we're going to divide each piece by 4, so we get x equals 12 divided by 4 is 3. Y squared divided by 4 you can write as y squared over 4 or 1/4 y squared. Okay, and the reason that that's important is because now I can set these two things equal to each other and solve for y. I know that I'm going to be in terms of y here. So y is going to equal 3 minus 1/4 y squared. And again, it is a quadratic, so I want to get everything equal to 0. In this case, I'm going to add the 1/4 y squared to the left and subtract the 3 because I like to keep my squared term positive if possible. It's just easier. So plus y minus 3 equals 0. And in order to go ahead and factor this, I actually don't want the 1/4 out front, so I'm going to multiply through everything by 4. So that's going to give us y squared plus 4y minus 12 equals 0. And that should make it easier for us to factor. So that's a y, that's a y. Factors of 12 are going to be 3 and 4, 2 and 6, 1 and 12. 2 and 6 is going to be the right combination. And the 6 is going to have to be positive. The 2 will be negative. So y is going to equal -6 or +2. So those are my bounds. So when I go ahead and take my integral, -6 to +2. Now we have to figure out which is the greater function. Don't go from the manipulated stuff here. Don't do that. What you want to do is you want to go back to these two functions right here to figure out which one is the greater function. So between -6 and 2 is 0. I'm going to plug that in. To me, that's the easiest. Plugging 0 into this one is going to give me 0. Plugging 0 into this one will give me 3. So the x equals 3 minus 1/4 y squared is the greater function. And then minus y dy. So there is nothing that I have to combine there, so we can go ahead and go straight to antiderivatives. So let's see, that will be 3y minus, that becomes y cubed, multiplying by 1/3, that gives us 1/12, minus 1/2 y squared, from -6 to 2. And some of these numbers are probably going to get kind of big here. 2 shouldn't be too bad. If I plug in a 2, we get 6 minus 8/12. 8/12 is going to reduce to 2/3. Minus 2 squared is 4. Half of that is 2, so minus 2. That one's not so bad. Minus the second parenthesis is going to get kind of big. 3 times -6 is -18. -6 cubed is -216 times a -1/12. I guess we'll reduce that in a second. So that'll be a plus 216 over 12. And then -6 squared is 36. Half of that is minus 18. That looks right, yeah. All right, let's start figuring this thing out. So in the first parenthesis, 6 minus 2 is 4. Minus 2/3 minus -18 and -18 is -36. 216 over 12, that definitely reduces because I know 2 goes into both. I think 4 might go into both. 3 definitely does. 3 is going to be 72 over 4. 72 over 4, that actually 72 over 4, that's 18. Well, that means 12 goes into 216 18 times. Okay, I definitely didn't know that, but that works. Okay, so now we've got negative 18 here. And we've got 4 minus 2/3 there. So the 4 minus 18 is 22. Minus 2/3. 22 in terms of thirds is 66. So that's going to give us 64 thirds. Pretty sure that's right, unless I made a mistake. All right, yeah, I'm pretty sure that's right. Okay, one more. Find the area between the curve y equals x and the curve y equals sine of pi x over 2. This one's not easy to do as far as algebraically. So kind of want to look at this one graphically real quick. The graph y equals x, we know, does this. The sine curve, however, we know starts at the origin, goes up, comes back down over here at pi, but it also goes backwards and does the same thing. So what we're looking at is the area between the regions here and here. So really, we're going to be looking at two separate integrals in this case. As far as finding the intersections, you'd have to set x equal to the sine of pi x over 2. And again, algebraically, this one would not be easy to do. So we're going to use logic instead. Use logic. So you can kind of tell where these things intersect by looking at them. 0 definitely is 1, because if you plug 0 in for x on both sides, you get 0 equals 0. What if I was to plug in x equals 1? Well, that would give me sine of pi halves on the right, which is 1 equals 1 on the left. Perfect. So it looks like 0 and 1 are definitely values. So x equals 0, that's the one that's kind of obvious. That gives us 0 equals sine of 0. That works. If x equals 1, that gives us 1 equals sine of pi halves. Sine of pi halves, again, that's 1. That works. What if x equals negative 1? Because it kind of looks symmetric. Well, that would give us negative 1 equals the sine of negative pi halves, which is really in the same place as sine of 3 pi halves. It is negative 1. So that one also kind of works. Okay, you're not usually going to get one where you kind of have to figure these things out like this, so don't stress about that, but it might come up where you have to use a little bit of logic to figure it out. All right, so this is a symmetric function. Okay, both of these functions are odd, meaning they are both symmetric to the origin, which means that if all I wanted to do, this is probably the easiest way to do it, is find the area of that one, then I can double it and I found the total area. So that's probably the best thing to do. So let's go ahead and just take the area from 0 to 1. Now graphically we've already shown it, but you can see that in this case the sine function here is the greater function. So it will be sine of, and we're going to write this as pi x over 2. Probably could have written it as pi halves times x, but minus the lower function x dx. So we're going to do this by symmetry. Now that's only half. So we need to multiply it by 2 in order to get both sides of the area. In order for us to do the sine of pi x over 2 part, we're going to have to do a u substitution. So u there would be pi halves x, which makes du pi halves times dx, which makes the dx part du over pi halves, or du times 2 over pi. So we're going to actually go ahead and split this integral up. So I'm going to have 2 times the integral. Now you can change the bounds or you don't have to change the bounds. I prefer to do that, so I'm going to change the bounds. Plugging in 0 for x is going to give me 0. Plugging in 1 for x is going to give me pi halves of sine of u times my new dx, which is going to be du times, oops, not 2 pi over pi, 2 over pi. That's the first integral. Minus the integral from 0 to 1, go back to the original bounds, of x dx. All right. From here, it should not be that difficult. So now we take the antiderivative of sine, which is going to be negative cosine. Oops, don't need that anymore. Negative cosine of u from 0 to pi halves. Oh, don't forget my times 2 pi. I'll bring that out front. That's a constant. Minus 1/2 x squared from 0 to 1. All right, so now let's just go ahead and simplify and see what we get. So I'm going to get a 4 over pi out front. Let's see, negative cosine of pi halves. Cosine of pi halves is 0, so that's 0. Minus negative cosine of 0 is going to be negative 1. Minus, plugging in the 1, you're going to get a half. Plugging in 0, you get 0. So on the left piece over here, I've got 0 minus minus 1, which is 1, times the 4 over pi, so that's 4 over pi, minus 1/2. And that's the area between that curve. All right, this video ran way too long, and I apologize for that. But again, that's how you find the area in between curves.